All right, so any issues with the ODP from yesterday? So let me see how we're doing today. That is up and running. And that is up and running. Good. All right, so let's take a look at yesterday's ODP and today's ODP. So yesterday's ODP, you were building a function called small that would assemble a small tree out of 3 integers and create 3 nodes with each of those values. And we pretty much talked about how to do that. So, you know, 3 malloc statements, one to create each of those nodes because they're created in dynamic memory. And then assign the data field in each of those nodes to match the arguments that were passed to the small function, and then set up the pointers on the left and the right. So the root has to point to the left node on the left and has to point to the right node on the right. And then the left and right children have no children of their own, so their left and right pointers are null. And then return the root of the tree, and that should have assessed 10 out of 10. Make sure, you know, if you want something to be null, set it equal to null. Don't assume it's going to be null. If you leave this off, there's a good chance that your assessment will still come out 10 out of 10, but Valgrind would complain about this, right? It would say uninitialized value being used. So make sure that, you know, if you want something to be 0, set it equal to 0. If you want it to be null, set it equal to null. All of that business. All right, so the next ODP is adding a root to, hey, glad you're here. 212 is adding a node to a root, right? So you're going to be passed a root node which has no children. It's just a, you know, a tree containing 1 node. And you're going to be given an integer, and you want to create a new node out of that integer and then tack it on to the left or the right of the root, right? So compare your integer n to the root's data value, and if n is smaller, tack it to the left. If it's bigger, tack it to the right. And do the same thing that you did in 211. Create a new node, set the data value equal to n. That new node's left and right children will be null, so set those to null. But then change roots either left or right child to point to your new node, depending on how n compares to the root's data. And that's 212. And 215 I may hold off on because, maybe not. We'll talk about it tomorrow. All right, but anyway, that's 212. That's due tomorrow. So that was 212. All right, so let's go through PA4. So PA4, you're building a binary search tree to construct a database of, in this case, license plates, right? And so, well, let me hop back on the server. Let me show you a sample. So if you look under /temp, there's a file called database.txt. That's a sample file that your program should be able to ingest. And the way this file is set up, there's 3 fields separated by spaces, right? And the only delimiters in here are white space. So a space, and a new line. Your name can contain punctuation, digits, backquotes, you know, dashes, things like that. Your license plate could be all letters, could be, you know, a number sign, could be a dollar sign, right? Don't make any assumptions about the data. It's a field of non-space characters followed by a space, bunch of non-space followed by a space, bunch of non-space followed by a new line. But the way we're interpreting this to talk about it, this is a license plate, a first name, and a last name. And your program will basically ingest this file and build a binary search tree that's keyed off of license plate. So this is what we're going to use when we compare nodes and decide should this node go to the left or the right of that other node. So after reading in this file, your program will have in its memory a whole binary search tree of license plates. And in each node of that tree, we have the license plate and also the first and last name of the person associated with that. All right, so that's the 40,000-foot view of your program, right? Ingest a database of license plate information, build a binary search tree, and then respond to user commands to let them interact with that database. All right, so your program is named plate 4, is named plate, right? And to run it, you say plate space and the name of the database file. All right. There's a sample program under /temp called plate 4, which you can use to see what the program should do, and we'll play with that in a minute. All right. So you run your program by saying plate space name of the database. If anything goes wrong at that point, print out the word error and exit with a return status of 1. Okay. What can go wrong at this point? If you just say plate, if you say plate with 3 arguments after it. If you say plate with something that cannot be opened as a file, right? Any of these things, those are errors. All right, so open the database file, ingested, license plate, first name, last name. The key is the plate, right? That's the thing you use to sort things in your BST. So again, you know, 3 fields separated by spaces. If you cannot read the database file, if you don't find 3 things, if you find an empty line, print out the word error, exit with a return status of 1. Okay, so the program is pretty merciless on the user, right? They do things right, or they get the error message and the program exits. All right. For the sake of reading in this file, you can make the following assumption. You can assume that each of these fields is no longer than 40 characters in length. Okay, and I won't test it with a file where, you know, somebody's last name is 500 characters. So you can assume these are limited to 40. But it's really important when you save this information in the tree, you don't just set aside 40 spots for each name and each license plate. We'll talk about that in a minute. But you're going to want to dynamically allocate on the fly enough space to store these fields in each node. So we'll come back to that. But that's what this boldface thing is here. All right, once you're running the program, what do? You basically look up license plates. So you type something in, hit enter, it looks for a license plate that matches what you typed in. And if it finds it, it shows you the name associated with that plate. If it doesn't find it, it says plate not found. But there's 3 other things the user can do. One thing they can do is they can type *dump, uppercase, 5 characters, enter. That will show you the contents of your binary tree. More importantly, it will show me the contents of your binary tree, right? So I'll use this to see what your tree looks like in memory. You can also remove a plate by saying *delete space license plate, and it will look for that plate in the tree, and if it finds it, it'll remove it. The other thing you can do is you can hit Control-D, which takes you out of the program after freeing your memory. All right, output details. When you do a license plate lookup, I want to see 2 lines of output. 1 line showing the first name and a separate line showing the last name. Right? This makes it easy to know that you didn't just store the whole name as a single string. So first name, last name, 2 separate lines. Right? And whatever you do, just keep prompting the user, enter a command or a plate. Right? Whatever they type in, if it's not a recognized command, it's a license plate lookup. So there are no syntax errors possible in this. Right? If they say *dump and they misspell it, assume they're looking for a license plate. So again, pretty heartless with respect to treating the user well. Whatever they type in, if it's not one of these commands, look up the license plate. If it's not there, say plate not found. Alright, so the dump command will show me a bunch of information about your binary search tree. And it should be formatted exactly like this. Tree height, colon, space, show me the height of the tree. Balanced, colon, space, followed by uppercase yes or no to indicate whether or not the tree is balanced. Blank line, LNR traversal, colon, and then show me the left node right traversal of your tree. One line per node. Plate, colon, angle bracket, license plate. Space, name, colon, space, last name, comma, space, first name. Right? Match this format. Do that for the whole LNR traversal, and then blank line, NLR traversal, pre-order, do the same thing. Blank line, LRN traversal, that's post-order, show the same thing. And we will talk about balanced versus unbalanced. We'll go through the code for that probably tomorrow. And the same thing for height, which is related. Yeah, visually, a balanced tree is one that's nice and full and fluffy, and filled in nicely at the lower levels before it starts getting lots of deeper levels. But we'll do the algorithms for that tomorrow. All right. If you want to confirm that your code is doing the right thing, run your code, feed it some commands, capture all of the output into a file, and then run the sample code /temp/plate4. With the exact same commands, capture the output to a file, do a difference on them. Difference will look character by character and see if things agree or not. And it's a smart function, right? If one character is missing from one file, it doesn't tell you the rest of the file is different. It will try to resync, and it'll do a pretty good job of saying, well, this one line was different and this line was extra, but everything else was the same, right? So if you don't want to try to figure out, is saying uppercase success going to be, as good as saying lowercase success, or what if I just make the first S uppercase? If you don't want to mess around with your points, right, just match the output of the sample program. All right, exiting, Control D at the beginning of a line signals end of file. That should cause your program to exit. Before exiting, it should free all the memory that's been allocated. So val grind it. Picking up an end of file will allow you to run your program and redirect input from an input file. So you could say, plate my database less than my test file 7, and it will read all the commands from my test file 7. And this is a really nice way to exercise your code. All right, implementation details. Here's the good stuff. So the node of your binary tree looks like this. It has 3 pieces of data, a plate, a first name, and a last name. And then it has 2 children, pointers called left and right, that point to the left and right subtrees. Again, the plate is the key. That's the thing you're using to decide where should I insert this new node. That's the thing you're searching for when you say, is this node in the tree? But along with that, in the same node as that plate, there's also the first name and last name associated with it. All right, you don't need to do the type def, but I'm going to do the type def throughout here, so it's easiest if you type def an uppercase node to be a pointer to a struct node. Okay, there's no sentinel with binary search trees, so in your main program, when you want to initialize your tree, if you're calling your tree root, just set it equal to null. Don't call it root. That's going to be confusing. Call it, my database or something like that, but just set it equal to null. Make sure it's a pointer to a struct node. All right. Do not assume that these strings are 20 characters, 20 characters, 20 characters, or 40 characters, or 1,000 characters, or anything fixed. Declare them to be char stars. And then when you need to put something in there, allocate space for that string. Okay, that's important. That's 15 points of your grade is dynamically allocating the stuff on the fly. So declare these to be just char stars, which means, this only takes 8 bytes because it's a pointer to a character. But it's not pointing to anything yet. So before I can string copy something into here, I have to allocate space. And basically use string length of string, right? So if I want to copy something into plate, I need to allocate space. How many bytes do I need? Well, it depends how big the thing is that I'm copying. So don't use size of, use string length, right? And add 1 to it to leave space for the null terminator. And that's super, super important. If you don't add 1, it's one of those things that'll work, 90% of the time and then suddenly fail. So if I'm copying, data into this car star plate, I would set plate equal to malloc 1 plus string length of data. So add 1 to the string length for your call to malloc. Alright, and when you're done, you have to free all of your memory, which means you're not just going through your tree and freeing the node, but first you have to free the memory that you allocated and pointed to each of these things. So we'll talk about how you free nodes in a tree, and it's pretty straightforward once we do recursion. But before you free a node, you have to free the fields in it that you also allocated. And Valgrind will tell you if you didn't do that. Alright, required functions. So I need you to implement the following functions. A height function takes the root of a tree, gives back the height as an integer. A balance function takes the root of a tree, gives back an integer flag. 1 means balanced, 0 is not balanced. An add function, which takes the root of a tree and then 3 strings, and adds that to the tree, returns the root of the tree. A search function, which is a little different. You pass the root of a tree and a license plate, and pointers to empty strings, or strings you don't care about. If the plate is not found, search will return a 0, and that's all that happens. But if the plate is found, search will return a 1, and these 2 fields, plate first and last, will contain the first and last name associated with that plate. So your search function will string copy the things that it finds into these 2 fields. So these come back from the function that you're calling. Delete simply takes the license plate, tries to remove it from the tree, and returns the root of the new tree. And so before you call delete, call search to see if the tree contains the thing you're trying to delete. Because delete does not tell you if the plate was found or not. Don't ever print information like that from your functions, okay? Print from your main program. Don't print inside your delete a message like, node not found. Because what if that's not what the person wants to do in response to delete? Right? But since delete can't pass back that information, don't call delete unless you call search first. Alright, 3 traversal functions, which we're going to go through after this. For in-order, pre-order, and post-order traversal of the tree, they don't return anything. And then a tree-free function, which takes the root of a tree, releases all the memory associated with it. So it frees the nodes and it frees the strings inside the nodes. So you got to have those functions. And each of these has to be fully documented, commented throughout, but also needs a header block right before indicating the name, list of inputs, outputs, behavior, and so on. And I'm going to give you specifics for that. So here's what I want your comment block to look like. I want function name followed by the name of the function, white space. Purpose followed by, in your own words, the purpose of this function, white space. Inputs, and then 1 per line lists the type of input, the name, and a description of what that input is. White space. Return, and then the return value from the function, or the word none if there's no return. White space, side effects, and anything else that the caller needs to know about what's happening inside your code. Now you can embellish this, okay, but this is a minimum acceptable example of a comment block for the add function. The goal here is, when you come along and you want to add something to your tree and you're going to use the add function, how many arguments do I pass? Well, bang, I can see there's 4 arguments, right? What are those last two arguments? Oh, okay, those are car stars. That's the first and last name. Side effects under here should also include, first and last name get modified by this function if, sorry, that's for the search, never mind. First and last are the things you want to add to the binary search tree, right? So this is not just an exercise in, add some more characters to your file. This is useful, right? This is like having a man page for a function that, in Unix we can say man string length, and it'll tell us how to use that function, right? Well, here you're putting the documentation for these functions inside your .c files, right? And I guarantee if you write these first while you're writing your function instead of putting them on at the end when you're all done, there'll be at least some point during your development when you'll come back here and it will help you understand the function you're trying to use. All right, so I want that for all of your functions, including these required functions. All right, we'll come back to suggestions and side note in a minute. Submission, plate PA4 on GitLab. Pay attention to the capitalization. The usual 24-hour offer. If you send me an email, plain email, my Clark email, not Canvas, not on the Linux server, but a regular good old email to my clark.edu account, send me an email saying, hey, can you download my repository, right? I will go ahead and I'll check, and I'll let you know yes or no, right? And you can do that at any time before noon tomorrow. And, once you do that, you don't have to worry about it. Just keep pushing your code over, and you're always set to go. And you won't be one of these people who, I try to download the repo and it's not there. Yes, Linux Mail is better than email, I agree. But, I try to do things through my Clark email so that it's actually, recorded and part of the public record and, all in one centralized spot and things like that. But yeah, I like Unix email. All right, so that's your submission. Put in your source files. Don't forget to include all of your source files and any .h files that you have and a make file. Okay. Don't include executables, binaries, object modules, things like that. But anything that you feel is part of your project, you can go ahead and put in that repository as long as it's not going to interfere with my making and running your program. All right, grading rubric. Here's the most exciting part, right? So the assignment is worth 100 points. Yes, these deductions will add up to a lot more than 100. That's okay. Nobody's going to lose points on all of these things. And if you happen to, right, you won't get lower than a 0. But here's the things that can cost points. If I can't download your repo by the deadline, 20 points. If I can't load it within 24 hours after that, it's 100 points off, right? So make your repo, send me an email. Don't worry about that. Makefile should build your executable. It should do, a nice clean build that only rebuilds things that have changed, and it should include a clean option. Okay, everybody's makefiles have looked fantastic, so keep doing what you're doing with makefiles, and keep doing that when you leave Clark and go on to a university, and your teachers are going to love you, right? So makefiles, I don't anticipate any problems. If I cannot compile your program, 40 points off, right? And if I can't fix the problem easily, right, it's potentially going to be 100 points off. If it's, something minor and I can fix it and compile it so that I can continue to test your program, I will do so, right? But you lose almost half the points. So always make sure after you've submitted everything, go back, re-download it, say make sure it builds the executable, and run it, make sure it does what it's supposed to do. Because, there's always cases where somebody decides to add a comment at the last minute, like their name or something like that. And, instead of saying / my name, they do one / my name, and now their code doesn't compile, right? So once you're all done, go ahead and recompile it, make sure that works. No warnings from the compiler, right? So that's 10 points. And warnings, usually they're not just being naggy. Usually if you're getting a warning, it's something you should probably do something about. If I cannot ingest the database file, 50 points off, because then it's really hard to test anything. If there's a problem reading the database file, you should give an error message. If not, 10 points off. If there's no arguments on the command line, you should give an error message. That's 10 points. If I can't look up a license plate, 30 points there. If you use fixed size arrays for storing the name and or the plate, that's 15 points, so make sure you use malloc. Delete. Delete is worth 15 points. Delete is the hardest part of this, right? And we'll probably get to the delete algorithm on Friday. Deleting from a binary tree is pretty tricky in some ways, and it's a lot of code and a lot of moving parts. Don't leave it till the last minute, but leave it to the end, right? Get everything else going first, and if you don't get anything working for delete, it's 15 points. It's not a big deal, right? If you get delete working, but it's not the algorithm that we've talked about in class, that's 10 points, okay? If your dump command does not work, that's half your points. Why? Because without the dump command, I can't look at your tree. You can tell me you're building a binary search tree and I can search for things, but I have no idea what your tree looks like, so you got to have a dump command working. Okay, so if that's not implemented, that's half your points. Height function and balance function, 10 points each. We'll go through those in detail. Those are absolutely trivial, right? Most of this code, the individual pieces are going to be really, really simple. You're going to print out 3 different traversals: in order, pre-order, post-order. Okay? If there's any issues with any of those, it's 10 points for each of those 3 traversals. So potential 30-point loss. Memory leaks or other issues from Valgrind, 15 points. And those are really important to nail down in this one because there's going to be so much stuff that's allocated on the fly. Control D gets you out of the loop, otherwise 10 points. If you do anything other than, look up license plates or respond to delete dump or Control D, that's 10 points, including if your empty line doesn't report an error, because an empty line is what it's trying to look up a license plate that's empty, or it's a syntax error depending on how you look at it. Plate not found, right? Issues in formatting your output, 10 points. No comment block in the main program with your name, etc., 20 points. Insufficient commenting, 10 points. I've not seen any issues with this. Commenting has been really nice. Keep up what you're doing. Issue with function comment block for any of the required functions, 10 points. And lack of consistent indenting, 10 points. And that's also been nice too. Guy who changes license plate to null. Yeah, that's cool. We were going to make a band when I was in college called the Null Devices, and we were going to be a null device from a different operating system. So /dev/null and NUL : and every OS has its own version of a null device. So wait, he got like 12,000 in fines for having a license plate that said null? Oh, sweet. That's pretty cool. No, you cannot get negative points on this. The lowest you can get is 100, but like I say, nobody's going to lose points for all of these things, right? So they don't add up to 100. Yeah, it's kind of like Little Bobby Tables then, the null license plate. Huh, that's pretty cool. There's got to be a way to work that. That would be interesting to try to come up with an assignment that would lose points for every one of these things. I don't think it's possible. Because if the dump command is not implemented, that I don't think you can have a problem with the LNR traversal, for example. Don't submit is just 100 points, right? Because it's not downloadable. But the challenge is, what's the maximum number of points you could lose? What's the assignment that would get the most deductions? That could be a good 223 assignment, actually, is figure out how to minimize the number of points. All right, so let's go back to suggestions. So this is a large project, okay? There are a lot of parts and pieces here, any one of which would be, potentially a formidable 224 exercise. There's a lot of stuff that has to come together for this. And it's really easy to get overwhelmed. Okay? Particularly if you're starting this, next Wednesday, it's going to be, just totally overwhelming. Because there are so many parts and pieces here. But even if you start this today, right, you can run into the empty screen syndrome of, going into your editor and it's like, where do I start? What should I possibly write first, right? And that's no fun, right? That's like the worst kind of experience you can have when you're trying to write code. Is just feeling like, I don't know how to do this, I don't know where to begin, I don't know how I'm ever going to finish this, I got physics homework to do, all that kind of stuff. So here's some suggestions, okay? This might be how I would go about working on this, but the general idea here is to break this into smaller, manageable pieces, okay? So first suggestion, build a tree by hand. Write a bunch of statements in your main program that basically creates a tree, right? So make your T node, do some hard coding of, okay, here's a license plate called 123, and the name is Mickey Mouse, and just create a node, call malloc with size of struct T node, and set the plate and the name to hardwired strings, and do that 3 or 4 times, make 3 or 4 nodes, connect them together into a binary tree. So draw your tree out on paper, connect them with just assignment statements, root left equals this node, and root right equals that node, and that node's left equals this other node, and make yourself a tree, right? Takes a lot of typing, but you do this once and you've got a tree. You don't have to worry about database files and ingesting and recursion, all this kind of stuff, right? So give yourself a tree, and then work on your traversal code, right? Because traversal will let you know what's going on in your tree. It will let you know the order in which things are stored. And we're gonna write some traversal code in a few minutes here. But write your in order left node right traversal. Okay? It's really like 4 lines of code. And if you've built a tree by hand, you can pass that to your traversal code, and it should print out the contents of your tree sorted by license plate. Okay? Now you got a really good feeling, right? You got something that's running, you're building a tree, you're in great shape now. Okay? At that point, go ahead and write your other traversal code. Node left right node. It's one change to the left node right code. Right? It's literally moving one line somewhere else in this 4-line program. And then your output functions are done, right? You can look at your data in different orders, okay? So what do you do next? Write your search function, okay? And test this with some more hardwired code. If you have a plate called 123, write a statement that's something like this: result equals search root comma quote 123 comma first comma last, where first and last are character arrays. And first thing your search function should do is just tell you if this plate's found or not. And then make it so if it finds it, it copies the first and last name from the tree into these variables. And once that's working, you can do something like this: if the result from search is 1, print out the word found and show me what the first and last names are. Otherwise, say it's not found. And now you can make several of these statements that look for all the plates in your file, look for some things that aren't found in your file, and make sure that's doing the right thing. So now you can completely develop and debug the search function. And a side note, if you're not comfortable with VI, this is a really good opportunity to get used to it, right? This is a lot of typing. If you're going to do this for 10 different nodes, this is a lot of typing. It's trivial in a modern editor, right? Like VI. I mean, you can copy and paste this and search for something in CW to change a word, and it would take you about a minute to write 10 of these blocks of search commands that print things out at the end. I say VI. I don't think VI even exists anymore. It's always Vim, but I just call it VI. But as long as it's not Vim tiny, it's all kind of the same. So play around with that, right? There's a video I posted a while back on the CSE channel on YouTube that goes through sort of slightly deeper VI commands for doing things by words and repeating commands and searches and things like that. It's a good opportunity if you're starting early to use it as an excuse to try to get a little better with VI. You really don't want to be sitting in insert mode and moving around with the cursor keys and deleting lines by backspacing over the whole line and so on. Your life will just go so much quicker if you learn a few of these commands and use them. And this is a really good place, since my suggestions involve writing lots of code that's going to be basically thrown away in the end. It's just code for development purposes. You don't want to spend an hour typing in that code or correcting typos to it. So that's a little sales pitch. All right, so you've got your search function working. What comes next? Your add function, right? Because the tree you've got so far you built by sort of hand wiring together nodes. Now make an add function. An add is not that complex, right? Call malloc, copy my and name into the first and last name after you allocate space for them. That's the trickiest part, right? And we'll go through recursive add functions tomorrow, and it's a pretty trivial algorithm. So the binary search tree part is the least worrisome aspect of this. And once you call add to add a new plate to your database, what do? Call your traverse function, LNR. And it should print the new tree, and you should see that it's still sorted by plate. And if you do that with 5 or 6 new plates that you add, and you call LNR and it's still sorted, you're probably doing the right thing in your add function. Now if you call your traverse LNR and things are out of order, then your add probably didn't put things in the right spot, right? But as you're developing it, your set of debugging tools is growing, which makes it easier to develop more. Okay, once all of that's working, now start with an empty tree. Instead of initializing your tree to the thing that you put together by hand, set your tree to null and start calling add. And the main trick there is going from an empty tree to a non-empty tree. Once it's non-empty, you already tested that. But if anything goes wrong, it's going to be when tree is null and you try to add something to it. Okay, once it's working, you can start dealing with the database file. So now we're going back to 224, fopen, fgets, fclose. Open up this file or whatever test file you're going to use. Read in your file. How do you read from this? Fgets, right? It's what you've been doing since you were born. Fgets, same arguments, but instead of standard in, use the file pointer that you got from fopen. And now you're going to read in a plate, a first name, and a last name. Just pass those as your arguments to your add function. And if you wrote your add function and you put documentation in there saying what the arguments are, you can go back and look at those. All right, at this point you can ingest the entire database, you can search for it, you can start comparing the behavior of the sample program against your program to see if, the tree traversal is coming out the same, to see if you're successfully inserting things and so on and so forth. Once all that's working, do your height and balance functions. We'll talk about those on Thursday or Friday, and those are pretty trivial. And then probably go ahead and work on your main program, because so far, all your stuff has been hardwired. Now make your main program. And what's your main program do? Deal with the command line argument, right? That's the name of a database file. Open the file and ingest it. You got that code working. And now just do a loop. Keep calling fgets until it returns null. And each time that you fgets a string, if it's a star dump, call your traversal code balance and height function. If it's a star delete, ignore it for now. If it's anything else, do a search. All right, once that's running, and when they do hit Control D and fgets returns null, free your memory and exit. So at this point, maybe do your free memory, maybe leave it for later, but don't forget it. And then work on delete, right? Leave that for the end. Because if you do delete wrong, you'll probably corrupt your binary search tree, and your other functions will look like they're not working either. So you want confidence that those functions are working before you start trying to do delete. So that when you call your LNR to see what's in your tree, you have good confidence that that's actually an accurate portrayal of what's in your tree. Okay, ask questions. Let me know if you're stuck or you're not sure what the next steps are. Build up on what you have. Start with something small. Keep adding pieces to it. That's a whole lot more fun than writing 200 or 300 lines of code and then trying to compile it and then trying to debug it. Right? So build this up in pieces. Your assignments are going to start getting more and more complex. 223, they'll be very complex. University, they'll be incredibly complex. Right? So this is an opportunity to start moving towards larger projects like that and thinking about how am I going to break this into manageable pieces? What are my steps? Right? What are my stepping stones that I can stand on and say, okay, wow, I'm done with all of that. Now I'm going to go forward in a way that doesn't require you to look back and you know, revisit things you've already done. So that's a big part of this assignment. You got to start early, right? This is not doable in 2 or 3 days for most people. So you really got to start early. Like today, you know. All right, and a quick sample execution. So I'll make a small database file just from the first 10 lines of that database file, and now I can run /temp/plate4 and I can give it that small database file, and I can start typing in commands. So I can say YGG155 and there's Claudie Powell, and I can say *dump and there's my 3 tree traversals. The tree has a height of 4 and it's not balanced. If I say *dump lowercase, what's it going to do? Plate not found. Anything that's not dump, delete, or end of file, it's looking for a license plate. If I just hit enter, plate not found. If I look for YGG156, bracket, plate not found. I can delete. If I delete something that's not in there, plate not found, uppercase. If I delete something that is in there, says success. And now if I dump again, that plate's not found in here anymore. And if I search for it again, it's not found. And then Control-D exits. All right, we got a few minutes left. Let's talk about tree traversal. So our goal is to, you know, take some tree that has stuff in it and print out the contents in increasing order, for example, if these are integers or something else ordered. And I want to talk about a traversal algorithm called LNR. This is in order. And this stands for left node right. Okay, how do we traverse this tree? It's trivial. You ready? It's 3 steps. Traverse that tree, print that, traverse that tree. That's the whole algorithm. Do you want to see it again? How do we traverse this tree? Traverse that tree, print that, traverse that tree. That's the definition of left node right traversal. Can we code it? Sure thing. So this was some insert code from last week where we were playing around with this insert function and moving down the tree and all that kind of stuff. I don't care about the insert function. I'm going to write a main program, right, that starts off with an empty tree and then just inserts a bunch of stuff into it. And I'm inserting it in random order. You know, this big negative number comes out here towards the end and so on and so forth. What I want to do in the next 3 minutes is show you how we can traverse this tree. So let me prototype my function. And let's write this function. Right. All right, so how do we traverse a tree? Traverse the left tree, print the root, traverse the right tree. Let's just do that. What does this code say? It does exactly what I was just doing with my hands. It says traverse the left subtree, print the root data, traverse the right subtree. Well, how am I traversing it? I'm calling this really cool function called LNR. Don't worry about the fact that this is part of the definition of LNR. You got to kind of put aside your suspicions for a few minutes. And here's the exercise, right? If you really believe that there is a function called LNR that traverses a tree correctly, then this statement will traverse the left subtree of root. This statement will traverse the right subtree of root. This statement will print the data of root, which means these three statements taken together should correctly traverse the tree called root. Now there's one thing missing from here. Think 215 base case. Eventually root is going to be null, and if root is null, trying to do root arrow left is going to throw a seg fault. So I'm going to put in one statement in here, which says if root is null, return. But other than that, that's the whole traverse routine. But I gotta call it with the root. Alright, you ready? Bingo, there's the data in your tree. So this is all there is to writing a left node right traversal. What's freaky about it is that it uses the left node right function inside it. Right? But again, if we believe that this function works correctly, then this function works correctly. Okay? That's the essence of recursion. So we will play with this a lot more tomorrow and Friday, but this is basically what we're going to be doing from here on out with trees. You just got to believe exactly, right? If I believe this function works, then hey, this code is perfectly correct. What is this code in? Oh, it's in this function. Well, good, that function must work then. All right, it's a little freaky, but that's the nature of it. All right, cool. I will see you next time. Have a good one. Thanks.